Okay, so to continue on with electron configurations, so far we've looked at how to do electron configurations for atoms in the S and the P block, and also probably atoms in the D block. But then you'll also be asked to do electron configurations for ions. So remember that ions are particles, atoms, or sometimes many atoms, but for now we're looking at single atoms that have either gained or lost electrons, and therefore have picked up a charge. So negative ions, which we can call anions, have added electrons. They've gained additional electrons. And positive ions, or cations, have lost electrons. So the anions are actually a lot easier and therefore probably really won't be asked about, I don't think. Maybe I've seen one, but typically you're not going to be asked so much about doing electron configurations with anions. And I'll try to explain why. So if you're doing an electron configuration for sulfur, and then you're doing an electron configuration for sulfur 2-, it's pretty straightforward because all you're going to do is add 2 more electrons to the next available spaces. Well, when ions are formed, they tend to form to fill out that outer valence shell. And so for a non-metal atom, something that has an incomplete, at least in this example, n equals 3 level, those extra 2 electrons are just going to go to fill out the remainder of the n equals 3 level. We know that filling electron energy levels gives stability. The noble gases have full outer shells of electrons and are incredibly stable and unreactive. So that's how ions tend to form. So when I am here with 3p4, I know that I can go up to 3p6 to have a full 3p level. And so adding 2 electrons, I'm just going to make the sulfur go from 3p4 to 3p6. Now this configuration happens to be the same as a noble gas. So this is the exact same as the configuration of argon. And so I guess they could ask you to do this, but every time when you do a negative ion and you do the configuration of the negative ion, you're pretty much always going to end up with the configuration of a noble gas, which means they probably can't ask you to do a noble gas electron configuration, an abbreviated one. They probably have to ask you to do the full one. Otherwise, yeah, you probably just end up putting down argon here. Or maybe you do neon, 3s2, 3p6. Let's try one more just so you see what I'm talking about. If we were going to do Br minus, now, so I've got Br. If I'm going to do the noble gas configuration, I would start with Ar in brackets, and then I would do, let's see, I'm in the 4, so I'd start with 4s2, 3d10, and normal Br is 4p5, because 1, 2, 3, 4, the 5th box over, 5th column over in the p block. Bromine is going to form a Br minus ion, and therefore when it becomes Br minus, I'm adding 1 electron, so all I have to do is fill out that last available spot in the 4p. And so this is the electron configuration of a bromide ion. So I suppose it's fair game. It's just not as tricky as doing the positive ones, and therefore it kind of seems less likely that they would do that. Okay. When you have a positive ion, you're going to be removing electrons because positive ions lose electrons. That's how they gain that positive charge. They lose the negatively charged electrons. Okay, so it's always a good idea to start with the electron configuration of the atom, even if they've asked you for an ion. So if they ask me for calcium 2+, I'd probably still recommend starting by writing out the configuration for calcium. So we've got 1s2 all the way through 4s2 here. And now when I see that calcium is a 2+ ion, I'm going to lose 2 electrons, and I'm always going to start from the outermost subshell first, the outermost sublevel. And so in calcium, the outermost level is pretty clearly the 4s2. Those are the only electrons in the 4th energy level. And so we can see that when I write the configuration for calcium 2+, I've just removed those 2 electrons. I removed 2 because the charge is +2, or 2+. Therefore, I need to get rid of 2 electrons. This gets a little trickier when we start to take away electrons from things that have d electrons, or from things further down the table that have s and p electrons that are forming positive ions. So let's check out some examples. So if you're asked to draw a configuration for vanadium, for a positive ion of vanadium, I would recommend start by drawing out the normal configuration of vanadium, the atom, the neutral atom. And so we can see that we're going to end up with 4s2 and 3d3 as sort of the ending part of the configuration. These are the highest energy electrons. Remember that those s and d are very, very close in energy at this point. Okay. Now, when we remove electrons, we remove from the outermost, physically outermost electrons first. And the electrons that are farthest away from the nucleus are the ones in the fourth energy level. The fourth energy level is outside of the third energy level in terms of its physical location from the nucleus. So we always remove electrons from the highest out energy level first and move our way in. So when I form a vanadium 2+ ion, I would start by just getting rid of the 4s2. I need to remove 2 electrons. There are 2 electrons in that outermost level, so I would get rid of those first. And so I'd be left with this configuration for vanadium 2+. If I go on to 3+, now I've already removed 2 electrons in the 4s2, and so then I have to start getting rid of electrons from the 3d, which is the next farthest out sublevel. So I take away 1 from 3d3, and I end up with 3d2. And from there on, we can see it would just continue. So if I'm vanadium 4+, I have to remove 4 electrons. The first 2 are the ones from the 4s, and then I would take away 2 from the 3d until I got to 3d1. And finally, for vanadium 5+, I would get rid of all of the 4s2 electrons, and I would get rid of all of the 3d electrons. That would be 5 electrons lost, leaving me with the configuration of argon here. So when you remove electrons, you always remove them from the highest, outermost sublevel first. So you're looking at the highest number shell. So the 4th shell is farther out than anything in the 3 shell. Let's see if we can apply that same thing here to germanium. So germanium is here. First, we draw out its full electron configuration. I can see that it's got 4s, it's got 4p, and it's got 3d. And so if we're going to rank these, the 4p are the outermost sublevel. And then the 4s are the second outermost. Those are the electrons that we would call the valence electrons because they're in the 4th energy level. So those are the electrons that we're going to remove first, and probably the only electrons that we will remove. If we had to keep going, we would then start taking from the 3d. But I've been asked for germanium 2+ and germanium 4+. For germanium 2+, I'm only going to get rid of the 4p electrons. And so I can see that everything else here is remaining for the germanium 2+ configuration. If I get asked to do germanium 4+, I now have to keep going. I would get rid of the 4p and also the 4s, and that would leave me with this configuration for germanium 4+. So with negative ions, you are adding electrons to fill out that shell, to complete whatever shell you're in. And with positive ions, you're removing electrons, but always removing from the outermost sublevel first. The last little bit is, what charge do these things form? I probably should have done this earlier, but I'm going to do it now. Typically, elements form particular charges in order to end up getting an electron configuration like a noble gas. So for things in group 17, they have 7 valence electrons. In order to be like a noble gas, they need to gain 1 electron. And so typically, things in column 17, the halogens, are going to form 1- ions. If we go then to the next to the left, these have 6 valence electrons. They typically form 2- ions. And then if we keep going, we'd expect these to form 3- ions. If we think of ourselves, if this is the 0, like on a XY axis, we've gone to the left, and that's how we're getting our negative charges. Just like going left on the x-axis, we'd get to -1, -2, and -3. If I go to the right, of 0, I end up back around here at group 1. And group 1, we know of 1 valence electron, so they tend to lose that 1 valence electron, and then they form 1 plus ions typically. Things in group 2 tend to form 2 plus ions, and things in group 13 are actually the ones that have 3 valence electrons, and they form 3 plus ions. Things in the middle here, in the D block, they always can form a 2 plus, and they often can form additional charges higher than that. The 2 plus is from the loss of their s electrons, their 4s or their 5s electrons, and then they can form higher charges when they start to also lose d electrons. So it's variable charges for most of the D block. Zinc, however, only forms a 2 plus charge, which is something the IB will expect you to know. Now, what about group 14? Well, actually, as we transition from metals to nonmetals down this zigzag here, we see that metals, which is this whole section of the table, metals really only form positively charged ions. They form cations. And so things like aluminum and then germanium and tin and lead, and even down here, Sb is called antimony, Bi, bismuth. These are all going to form positive ions. They're not going to form negative ions. And even in your data booklet, phosphorus is showing a +5 charge rather than a 3- charge, although I do believe a 3- charge is also possible. But the further down they are in the table, the more metallic they are, the more likely they are to form plus ions. So things like germanium and tin and lead, they don't form 4- ions. They tend to form +2 or 4 plus ions for this group here. Whereas if we're up here at the top, things that I'm highlighting in purple, these are more non-metallic elements, so we would expect these to form more of these negative ions. Carbon, not very commonly forming an ion, probably can form both 4- and 4+ under the right conditions, but silicon more likely to form 4+ than 4-, but they're kind of in between. I wouldn't worry too much about group 14 in terms of ion trends, but I would know group 1, 2, and 13 as 1+, 2+, 3+, and I would know groups 17, 16, and 15 as 1-, 2-, 3-. So those are the trends for ions. If they tell you to write the configuration for the potassium ion, they're going to expect that you can look at where potassium is in the table and work out that it's going to form a 1+ ion. Same thing goes for oxygen. If they say figure out the configuration for the oxide ion, they expect you to be able to come up with oxygen's going to form a 2- ion, and then you can work out the configuration from there.